Welcome to Chapter 2 of Class 10 Science, Acids, Bases and Salts. In this fascinating chapter, we'll explore why lemon tastes sour and baking soda tastes bitter, how we can identify acids and bases using indicators, and the important role these substances play in our daily lives. Have you ever wondered what to suggest when someone suffers from acidity after overeating? Lemon juice, vinegar, or baking soda solution? The answer lies in understanding how acids and bases neutralize each other's effects. Throughout this chapter, we'll conduct exciting activities, understand chemical reactions, and discover how salts are formed and used. Get ready for an amazing journey into the world of acids, bases, and salts. Let's begin by learning how to identify acids and bases using indicators. Indicators are special substances that show different colors in acidic and basic solutions. Natural indicators like litmus, turmeric, and red cabbage leaves, as well as synthetic indicators like phenolphthalein and methyl orange, help us distinguish between acids and bases. In Activity 2.1, we test various acid and base solutions with different indicators and record the color changes. Blue litmus turns red in acids but remains blue in bases, while red litmus turns blue in bases but stays red in acids. Phenolphthalein is colorless in acids but turns pink in bases, and methyl orange shows red in acids and yellow in bases. We also have olfactory indicators like onion, vanilla, and clove oil, which change their odor in acidic or basic media. These indicators are incredibly useful in laboratories and everyday life for identifying the nature of substances. Now let's explore the chemical reactions of acids and bases. Acids react with metals to produce hydrogen gas and salts. In Activity 2.3, when zinc granules react with dilute sulfuric acid, we observe bubbles of hydrogen gas that burn with a characteristic pop sound. This reaction gives us zinc sulfate and hydrogen gas. Acids also react with metal carbonates and hydrogen carbonates to produce salt, water, and carbon dioxide. In Activity 2.5, when we add hydrochloric acid to sodium carbonate, carbon dioxide gas is produced, which turns lime water milky. The most important reaction is neutralization, where acids and bases react to form salt and water. In Activity 2.6, when we add hydrochloric acid to sodium hydroxide solution with phenolphthalein indicator, the pink color disappears, showing that the base has been neutralized. Metallic oxides react with acids to form salts and water, similar to bases, so they are called basic oxides. Non-metallic oxides react with bases to form salts and water, similar to acids, so they are called acidic oxides. What makes acids acidic and bases basic? The answer lies in the ions they produce in water. All acids produce hydrogen ions H+ in aqueous solutions, while all bases produce hydroxide ions OH-. In Activity 2.8, we test the electrical conductivity of various solutions and find that acids conduct electricity because they produce ions, while substances like glucose and alcohol containing hydrogen don't conduct electricity because they don't produce H+ ions. Water plays a crucial role. In Activity 2.9, we see that dry HCl gas doesn't affect dry litmus paper, but HCl solution turns blue litmus red because H+ ions are produced only in the presence of water. These H+ ions combine with water molecules to form hydronium ions H3O+. When we dilute acids or bases with water, the process is highly exothermic, and we must always add acid to water slowly with constant stirring, never water to acid, to prevent dangerous splashing and container breakage due to excessive heat generation. Now let's understand how we measure the strength of acids and bases using the pH scale. The pH scale ranges from 0 to 14 and measures the hydrogen ion concentration in a solution. Values from 0 to 6 represent acidic solutions, with lower values indicating stronger acids. A pH of 7 is neutral, and values from 8 to 14 represent basic solutions, with higher values indicating stronger bases. We use universal indicator, which is a mixture of several indicators, to measure pH. It shows different colors at different pH values. Common substances have characteristic pH values. Gastric juice around 1.2, lemon juice around 2.2, pure water at 7.0, blood at 7.4, milk of magnesia at 10.0, and sodium hydroxide solution at 14.0. The strength of acids and bases depends on how many H+ or OH- ions they produce. Strong acids like HCl and H2SO4 produce more H+ ions, while weak acids like acetic acid produce fewer H+ ions. Similarly, strong bases like NaOH produce more OH- ions than weak bases like ammonium hydroxide. pH plays a crucial role in our daily life and environment. Living organisms can survive only within a narrow pH range. Our body works between pH 7.0 to 7.8. When rainwater has pH less than 5.6, it's called acid rain, which harms aquatic life when it flows into rivers. Plants require specific pH ranges for healthy growth, and farmers often test soil pH and adjust it using materials like quicklime or slaked lime. In our digestive system, the stomach produces hydrochloric acid with pH around 1.2 to 3.0 to help digest food and kill bacteria. When excess acid causes indigestion, we use antacids containing mild bases. Tooth decay starts when mouth pH falls below 5.5, and basic toothpastes help prevent this. Many plants and animals use chemical warfare for defense. Bee stings contain acid that causes pain, relieved by baking soda, while nettle leaves inject methanoic acid, traditionally treated with dock plant leaves. Nature provides perfect neutralization solutions. Let's explore more about salts, their families, properties, and uses. Salts can be grouped into families based on common positive or negative ions. Sodium salts like NaCl, Na2SO4 belong to one family, while chloride salts like NaCl, KCl belong to another. The pH of salts depends on their parent acids and bases. Salts of strong acid and strong base are neutral, salts of strong acid and weak base are acidic, and salts of weak acid and strong base are basic. Common salt, sodium chloride, is obtained from seawater or rock salt and was historically important, as seen in Mahatma Gandhi's Dandi March. It serves as raw material for many chemicals through processes like the Chlor-Alkali process, where electricity passed through brine produces sodium hydroxide, chlorine, and hydrogen, all useful in various industries. Bleaching powder, made from chlorine and slaked lime, is used for bleaching and disinfection. Baking soda, sodium hydrogen carbonate, is used in cooking, antacids, and fire extinguishers. Washing soda, sodium carbonate decahydrate, is used in glass, soap, and paper industries. An interesting property of some salts is water of crystallization, fixed water molecules present in their crystal structure. In activity 2.15, when we heat blue copper sulfate crystals, they turn white as water molecules are removed, and we can see water droplets in the test tube. Adding water restores the blue color. Copper sulfate has 5 water molecules, gypsum has 2, and washing soda has 10. These water molecules are chemically bound, not just making the salt wet. When we heat gypsum at 373 Kelvin, it loses water molecules to form plaster of Paris, which doctors use for supporting fractured bones. When mixed with water, it sets back to gypsum, forming a hard solid. This half-water molecule notation means two formula units share one water molecule. Plaster of Paris must be stored in moisture-proof containers to prevent premature setting. Understanding these properties helps us use salts effectively in various applications. Let's review the key concepts from this chapter. Acids produce H+ ions in water, have sour taste, and turn blue litmus red. Bases produce OH- ions in water, have bitter taste, and turn red litmus blue. Indicators help identify acids and bases through color changes. The pH scale from 0 to 14 measures hydrogen ion concentration. Neutralization reactions between acids and bases produce salts and water. Salts have various uses in daily life and industries. Water of crystallization is the fixed number of water molecules in a salt's crystal structure. Important chemical processes include the Chlor-Alkali process for producing NaOH, Cl2, and H2, preparation of bleaching powder from chlorine and slaked lime, formation of baking soda, and production of plaster of Paris from gypsum. These concepts find applications in healthcare, agriculture, industry, food, and environment, showing how chemistry impacts our daily lives. Thank you for learning about acids, bases and salts with SilentReader Science. We hope you enjoyed this comprehensive journey through Chapter 2. Remember the key takeaways. Acids and bases have characteristic properties identified using indicators. pH scale measures acidity and basicity. Neutralization produces salts. Common salt is raw material for many useful chemicals, and water of crystallization gives salts unique properties. In our upcoming videos, we'll explore metals and non-metals, carbon compounds, periodic classification, and much more. Subscribe to our channel, like this video if you found it helpful, comment with your questions, and share with your classmates. As Marie Curie said, nothing in life is to be feared, it is only to be understood. Keep curious, keep learning, and keep exploring the wonderful world of science with SilentReader.